Welcome to session number 40. In today's session, we're going to be continuing our discussion of the MOS field effect transistor, the MOSFET, and we'll be continuing our discussion on some what one would consider generally as second-order effects, generally not discussed in a very basic course. We'll be looking at sub-threshold operation and specifically sub-threshold swing. We'll be defining what these things are, and then we'll be looking at some final thoughts on the regions of operation. Remember, the regions of operation of the MOS cap are accumulation, depletion, weak inversion, and strong inversion. For the MOSFET, the regions of operation are generally weak inversion and strong inversion. And finally, if we have time, we'll be starting our discussion on channel length modulation, which we discussed qualitatively in session number 39. So to get us started, we'll be returning now to the greatest love story ever told, Rodolphe the poet, Mimi the flower girl, La Bohème, and we'll be listening to the magnificent aria, They Call Me Mimi, and we'll see you in about 3 minutes. Welcome back, and let's get started with today's session, session number 40. We'll be focusing mainly in what is known as weak inversion or subthreshold operation. You can see the first three topics involve that particular region, and then if we have time, we'll be getting into chapter 22. All of these particular sections are in chapter 21. Chapter 22 starts with channel length modulation, and at the end we'll be looking at a video clip which I think you'll find amusing, if nothing else. Okay, so let's get started on subthreshold operation. This is a reprint from chapter 18, which discussed the MOSFET and weak inversion from an energy band diagram standpoint. Involves that point where the intrinsic and the Fermi level just cross, that's point 1, to where the intrinsic level goes down below the Fermi level as much as it was above the Fermi level in the bulk. So in this particular case, we have a doping of 10 to the 17th, and this distance right here would also be 0.42 electron volts. And all that is controlled by the gate voltage. If the gate voltage is such that we have the intrinsic level touching the Fermi level, then we have a little bit of band bending, and as we increase the gate voltage in a positive sense, the band bending increases until we get to point 2. At point 1, the depletion region is maximum, and as the gate voltage increases, more and more negative electrons, of course negative electrons are negative, electrons are attracted to the surface, and the surface has a mobile layer of electrons until we get to point 2, which is a threshold where it has 10 to the 17th per cubic centimeter of electrons. So if we go back to, again, this is chapter 18, and we look at the electric field for the entire region. Remember, we solved the Poisson's equation and we found the electric field. This part involves negative band bending, so this is accumulation. This term here, these three terms involve a situation where phi is positive, and this is the region that we're going to be interested in. You notice the symmetry, which is kind of nice. Now, for weak inversion, this term is basically zeros. This term was put in there just to make it symmetric. It's not terribly important. So these are the two terms that we have for weak inversion, and you notice that we have a combination of an exponential term and a linear term. Those are really hard to work with. So basically, we are going to neglect the linear term and only consider the exponential term. Okay, so given the electric field, we can use Gauss's law, because Gauss's law tells us that whenever we have electric field, we must have charge, which produces the electric field. And the variation between the electric field and charge is just the permittivity. So we can write an expression without too much hassle or burden for the charge, and this is the mobile charge at the interface right here, and that is a function of the band bending. So what do we do with it? Well, this is our starting point, and we need to massage this a little bit because this is the mobile inversion charge as a function of band bending, and even if we're somewhere between point 1 and 2, where the simple theory says we should have no band bending, we should have no charge at all. But of course we know that's not true. We do have charge we do have band bending, but we want the band bending as a function of the gate voltage, because that's the knob that we can turn, and we also want it when we apply a drain voltage, a VDS, we want it as a function of the channel voltage. And so we can write equation 2156, which puts it in a much nicer form. Eventually we have to get this phi into V sub G. Let's wait on that, have a little bit of patience. Okay, but we do need the channel voltage, and here we have the inversion charge, which says that channel voltage increases, the inversion charge decreases, because the band bending becomes less and less as we move along the channel. Now, we don't show the channel here. It is in and out of the paper. So we'd have to have a third dimension going out with the source and going in with the to the drain. So, like we do in so many cases, we want to check to make sure our units are right. So let's see if the units work out here. This is unitless because it's centimeters to the -3 divided by centimeters to the -3. This is always unitless, so we don't have to worry about that. So really we're interested in this term. This is KT over Q is in volts. And so let's see what the units of all of this stuff is right here. Well, all of this right here in the numerator is just Q dep. It is an expression we've seen a number of times before. So this is Q dep to the 1/2 power. This numerator to the 1/2 power is Q dep, and of course divided by phi, so phi is in volts, so everything works out quite well. So that's a good thing. So we have all the elements. We have mobile charge, and we have now we're going to put a voltage, VDS. So we're ready to have some current. Well, there's two issues before we get to that we want to emphasize. At the source, we have a barrier, and the barrier is due to the fact that at the source, right here, we have a source contact, which is N+, and if we're somewheres in this region right here, we have a little bit of N, but not very much. So the N+ source is going to have it's going to be degenerately doped, so it's going to have a barrier of about 0.56 electron volts, which is 1/2 the band gap. And if we're somewheres in weak inversion, we may be able to reduce that just a little bit, but not very much. So we're going to have a barrier at the source of somewheres around 0.5 volts. Now that will drop as VG increases till we get to threshold. The barrier doesn't go away. It becomes, and we'll see this later on, and we've already hinted at it in the previous session, we have a barrier of about 0.14 volts, which is still significant. But certainly in weak inversion, we have a significant barrier. So not too many electrons are able to overcome that barrier. So that's one big deal. The other big deal is what happens to I should just mention before we move on, the whole region of weak inversion, we have something called an isojunction, because both the source contact, the degenerately doped source, and the channel are N-doped. So that's what we call an iso, or same junction. It's not really a PN junction. For those few electrons that can surmount the barrier, well, what do they? They certainly see an electric field, but they also see a concentration gradient, because as we move down the channel from the source to the drain, the number of mobile charges gets less and less. So it's maximum at the source, and it's minimum at the drain, and it is that concentration gradient difference which can move the electrons not by so much by drift, because there's so few of them, there's not going to be much drift, but there's going to be a lot of diffusion. So we have a diffusion current generally in weak inversion. And that diffusion current is going to change over to a drifted current as the gate voltage increases in a positive sense. So what we want to discover right now is, what is this current? What is this diffusion current? Well, we write the basic equation for current. Current equals the current density multiplied by the cross-sectional area. Cross-sectional area is the thickness of the mobile inversion layer multiplied by the width. That's here. This is T inversion multiplied by W is A, and the current density is NeV, where V is the velocity. This goes back to our first session. We've seen it many, many times. It's the basic equation for current, and we write the velocity is equal to the mobility multiplied by the transverse electric field. That's something we talked about in our last session. And of course, the transverse electric field is just the first derivative of the channel voltage as a function of Y with respect to Y. So putting all that stuff, including our Q inversion, into this equation, we get equation 2158. The NE is now Q inversion, which is in coulombs per square centimeter, divided by the inversion layer thickness. So this here is in coulombs per cubic meter. We see that the T inversions cancel out, which is very nice because we can't even measure it. It's a very small number indeed, and we get our IDS times dy is equal to the right side of equation 2158, and we're just ready to integrate. This is a very easy integral because we're integrating from the source to the drain. That's why the L appears here, and we just integrate the Q inversion, which we have right up here. We just stick that in, again as a function of band bending now. So that's how we're going to perform the integration. And that's a relatively easy integration because we only have one term here which has the channel voltage, and that is our variable of integration. So we just perform that integration, and here it sits, and we're integrating from 0 to VDS along the channel. That's why we have a VDS here, and everything else is pretty straightforward. And again, we always get this combination U, W over L. We're going to see we also have a Cox in there, but that's not shown explicitly here. For VDS greater than about 0.1 volt, this term basically goes to 0, and we have equation 2160, and here it sits. So the approximation sign is relevant because this term should be there, but it's so small that we neglect it. Now we're going to go through this one more time, this exercise one more time, because we need to modify this equation, because I really want to stick in the gate voltage here. I don't like band bending because it's not a knob that I can turn. It's a consequence. It's not a prime source. The prime source, the thing that we control, is the gate voltage. So we're going to go through this exercise making an alternative derivation using our basic equation for diffusion current. This is diffusion current, kind of like a wolf in sheep's clothing. This is a situation where we're going to start with the basic equation for diffusion current as a concentration gradient. And we've seen this a number of times. We usually see it J diffusion without the A, Here we're going to include the A. D is the diffusion constant, and of course Q is just the electron charge, 1.6 times 10 to the minus 19 coulombs. We can use the Einstein relationship, D over mu is KT over Q, with that nice little rhyme, to eliminate D, and we know that the area is W, the width of the device, multiplied by the inversion layer thickness. So equation 2161, we put all that good stuff in there. This is the Einstein relationship here. This is the area, and the Q comes from here. So again, if we look at the units of mu are centimeters squared per second. This is volts. This is centimeters squared. And this term here is coulombs. That's where the Q is, divided by c to the fourth. The units of N are c to the minus third. Units of Y are centimeters. So the total units here are centimeters to the minus fourth. And if we put all that stuff in, we get coulombs per second, exactly as we would have expected. There's certainly no big surprises there. This is exactly the kind of procedure that we followed for the currents in a bipolar junction transistor. So now we assume that the concentration gradient is equal to the concentration at the source, where L equals 0, minus the concentration at L, the drain, divided by the distance. Well, distance, of course, is just L. And we're making the assumption here that no charge is created or destroyed. Certainly not created, but it's also not destroyed as we move from the source to the drain. That's exactly the assumption we made in the BJT, that there's no recombination in the neutral source. So we put in 2163 into 2162. We have the two values at the source and at the drain. The only difference is that at the drain we have VDS for the channel. So now we have equation 2162 becomes what we have here is 2165. And so 2165 is beginning to look at like 2156. You can scroll back to take a look at the differences. We still have a 5. That's a pain in the neck. We're going to deal with that in just a little bit. But we also have some other terms that are rather not very pleasant. And this one right here, T inversion, is the one we have to get rid of. The L here comes from this L up here. Okay, so let's now attack this inversion layer thickness. And we're going to do that with the energy band diagram. Notice that the bands bend down. Presumably the intrinsic level is a little bit below the Fermi level, so we do have a little bit of mobile carriers at the interface, and we have lots of depletion region charge in this region. Okay, so we're going to take this thing, even though it looks like it's parabolically bent, and we're going to assume that it's more or less a triangle. In fact, it's a triangle not over the whole distance here, but just over this distance right here. So I probably should have made this dotted circle even quite a bit smaller, but then you wouldn't even see it. So think about this triangle as being right at the surface. So the T inversion would be the horizontal line. The vertical line here is energy. In fact, it is how many electrons have enough thermal energy, that's what KT over Q is, thermal energy, to overcome the barrier and to participate in conduction from the source to the drain. The slope of this line here, not the hypotenuse, but this slope of the line, the slope of the angle alpha, is equal to the electric field. And we know that because electric field is equal to energy divided by distance. The energy is the thermal energy, and the distance is T inversion. So really what we want to do now is find the slope of the angle alpha, which is KT over Q divided by T inverse. And that would be the electric field, or another way of looking at it is a T inverse equals KT over Q divided by the electric field. So if we can find the electric field, we are really in good shape. And we do that by using Gauss's law and making the following assumption, that in subthreshold, in weak inversion, the vast majority of charge is depletion charge. So we have positive charge on the gate, negative charge in the depletion region, and all of the electric lines end in the depletion region, fixed ion charges. So, as a development here, it's fairly straightforward. The Q depletion is equal to the WD, which is this distance right here. It's not WD max because we haven't maxed out yet, multiplied by the charge density. So it's coulombs per cubic centimeter multiplied by width is coulombs per square centimeter. We found the width many, many times. We actually have a way to guess it if we forget about it. It's fairly straightforward. And multiplied by Q and A. So this is the Q depth, and we've seen that quite a number of times. So Gauss's law tells us that, go back to here, that the electric field is equal to the permittivity multiplied by the charge. Whenever we have charge, we have electric field. Whenever we have electric field, we have charge. They are related by Gauss's law. So we have an expression for Q depth, and now we just find the electric field by dividing by the permittivity, and there it sits. This is the electric field, and we just basically ram this back into here, and we find Q inversion immediately, and here is Q inversion. And if we put in this back into this equation here, we get equation 2156. And you can see that for yourself. And that's a good thing. The only thing we have to deal with now is this bad boy right here. So we're almost there. So now we go on to the really interesting, important subject of subthreshold swing S. And what we do is we start with 265 right here, but we put in the expression we found for T inversion. And that we call equation 269. Here, there's no T inversion, so that's a really good thing. This is the problem right here. And if we look at, I guess you'd call it an alternative form of this expression, and this is the way it generally will appear in most textbooks. The coefficients we're going to be dealing with in just a minute or so. The important part is we've been able to transform phi into v, and that is really the critical part of this. So let's take a look at these two forms and see if they give the same units. They better give units. Overall, they have to give units of Coulomb per second, but let's see if the units are correct. We don't have to worry about this. We don't have to worry about this because this is all unitless. We don't have to worry about the Ni over Na squared. We don't have to worry about the KT over Q squared because that's the same. Basically, all we have to do is compare this term to, of course, M is dimensionless, to this term here. W over L goes out, mu goes out. So we want to see if C ox is equal to this guy here. And we do that by putting in the all the units. The units of permittivity are coulombs per volt centimeter. The units of NAQ are coulombs per cubic centimeter. And of course, V is in volts. And we get coulombs per volt centimeter squared. And if we put in the units for mobility, guess what? We get the right units of coulombs per second of current. And for equation 270, which we didn't actually derive, it's a little bit of a pain in the neck. Can be done. I have it in my notes, but I'd rather not go through that now. COX has exactly the same units of coulombs per volt centimeter. So the units are the same, and we can conclude that the probability is that the equations both give current and they're both correct. And now we've got to deal with the problem up here, band bending, and to put it into gate voltage. So just moving right along, we want to get rid of this term. It's not really a big deal because we have diffusion current here. So for VDS more than, 0.1 volt or so, this should be, if this is 1, it's not right. I'm sorry, 0.1 volt. So if it's, VDS is greater than 0.1 volt, this term goes to 0, and the whole thing in parentheses goes to 1. So this is the equation that we want to take a look at in more detail. And fortunately, we can relate phi to the gate voltage by using a little trick. The total voltage, probably should have put, this is VG, and it is dropped across T oxide and it's dropped across the oxide capacitance and the depletion capacitance. So if we have a voltage from here to here, plus to minus, the Q here, because they're shorted, is the same. So whatever Q I have here, I must have here. We did capacitors in series, but we used that principle. So the Q is the same for the two capacitances. Of course, the capacitances are unequal. This is a very pessimistic picture. I should have made these lines closer than these lines because I want C ox to be much bigger than C dep. So it looks like that's not a very good choice of spacing here. Anyway, so if I increase the gate voltage, the voltage across the series combination, the delta Qs are the same. The only differences are the C oxes. And this guy right here is delta V, because charge divided by capacitance is voltage. So this is now my important term, and I divide out by delta phi, and I get 1 plus delta Q over C ox divided by delta phi. Well, what is delta Q over delta phi but just C dep? So this looks very familiar. Hopefully, this is just our parameter M, our dimensionless parameter M, which is always greater than 1. And this is an important result because it says that I can toggle between gate voltage and band bending simply by multiplying or dividing by the parameter M. So the band bending is now given by VG minus the threshold divided by M, and there's another relationship which you can see, which makes a lot of sense. I won't actually say too much more about it. This relationship to 2173 is the starting point for something here. Starting point to convert this guy into this guy. So we won't do that now, but if you want to do that, this is where you start. Okay, so now I can write the drain current. This is diffusion current in subthreshold or weak inversion using VG minus V threshold divided by M. Now, one can argue that the coefficient here, the exponent, is negative because VG is less than V threshold, and that's true. However, the point is that when I raise the gate voltage, this term becomes more and more positive, more and more electrons are able to overcome the boundary, and then they diffuse, not drift, they diffuse to the drain by diffusion current. Okay, and we can summarize the whole bit by figure 21.7, and if we have a log of IDS, it is proportional to the power right here. And that would be a straight line. We're taking the logarithm, either the natural log or the log to the base 10. We basically just bring this term down, and we get a straight line as a function of Vg. So in subthreshold, we get a straight line, and that's diffusion current dominates. It's all diffusion current down here, and as we increase the gate voltage and we approach V threshold, we start getting a little bit more and more drift current until we get into strong inversion, and in strong inversion we get drift current only. And we can summarize that in two proportionalities. In weak inversion, the Q inversion is proportional to exponent of e to the Vg over nkt, and the IDS is also proportionate to the exponent. That's why we have diffusion current, same exact thing that we had in the bipolar junction transistor, whereas in strong conversion, the Q inversion is proportional to the difference between Vg minus V threshold, not the exponent, and the IDS, the drain current, is proportional to Vg squared. Okay, now it would certainly make sense, and it's true, that the coefficient of the current determines where the y-intercept would be, but we're not really interested in that. What we're interested in, of course, that depends on where I have the 0 point for the gate voltages. So this point right here where it touches is not terribly important. What is important is the slope. And we suspect that the slope, I should say the slope of the log of the drain current. And we suspect that the slope is going to be dependent on this factor in the exponent. Now, let's compare the operation in weak inversion to the operation of BJT in the forward active mode. And remember, in the forward active mode, the collector current is approximately equal to the emitter current. The difference, of course, is the very small, hopefully very small, base current, and it's proportional to Q VEB divided by KT. Let's remind ourselves why I put the EB and not the BE. This is for a PNP. So for PNP, the emitter is at a higher potential than the base, because P for the emitter, we put a positive potential on the emitter, which forces the depletion region to be smaller. Positive will push, not pull, but push holes from the emitter into the base. So VEB would imply that we have a forward bias on the emitter with respect to the base. So the base, the emitter-base junction is forward biased. If it was BE, then we would suspect that we have an NPN. So that's really not important. But anyway, taking the log of IC, it's pretty straightforward. Just bring down the coefficient, and we do the relatively simple algebra. And we find, as we must find, that we get 1 over 60 millivolts. And that, of course, is our very well-known number. If we take the inverse of that bad boy, we get 60 millivolts on top. So for a BJT, the slope of the collector current versus the emitter base bias is 60 millivolts, and so this is the input, which would correspond in a MOSFET in weak inversion to the gate voltage, and this is the output current, which in a MOSFET corresponds to IDS. So let's do the same thing for a MOSFET, and as we probably can guess, here's the calculation right here, it's going to involve M. So the same thing we do for the BJT, we do for the MOSFET, and we get an extra factor of M. So if we compare the MOSFET to the BJT, it looks like the BJT wins, because the BJT gives us 60 millivolts, but for the MOSFET, we get more than 60 millivolts because we have an extra factor of M. So all that's summarized here in this picture. We want a large slope. A large slope would be, the largest we can think of would be 60. That's not possible because M must be greater than 1. A poor swing would have a much higher value. And since M is like 1.1, so 10% over 60 would be about 70. So 70 would be a reasonably good number for the swing. So just to summarize here, this sentence is important. In the MOSFET, in weak inversion, not all the gate voltage is going, so we can summarize this in one, I would suggest, rather important sense. In the MOSFET, in weak inversion, in subthreshold operation, only a percentage of any increase in gate voltage results in increased mobile inversion charge. Some of it goes where we don't want it. That is increased depletion width. Don't forget the depletion width has not reached its maximum value in subthreshold. It only reaches its maximum value when we get to strong inversion. So in that sense, the BJT is somewhat more efficient. And there are other ways also in which a BJT has some advantages over a MOSFET. Okay, now I'd like to return to an example that we did previously. But we'll just go through it very quickly again. It's an NMOS p-substrate silicon, doped or default doping 10 to the 17th. It has a moderate gate oxide. Today, this would not be about 34.5, more like 15 or 20. But the numbers work out very nicely, 10 to the minus 6 for the aerial C-ox. So the flat band potential for 10 to the 17th, if we have an N plus poly gate, is 0.56 for the N plus poly gate plus 0.42. So it's just about 1 volt of flat band voltage, minus 1 volt. And the threshold then is just over 0, very close to 0. Now, the condition for a little bit of inversion, the band bending of the surface, or I should say, I'm sorry, condition for strong inversion, I should have written here strong inversion, is the band bending of the surface is twice the bulk band bending. However, if we start an intrinsic, instead of starting at the threshold, we start where the Fermi level just crosses the intrinsic. Instead of 2 phi b, it's just phi b, 0.42. For 10 to the 17th, and then we get minus 0.44 volts. So a gate voltage of plus 0.02 brings us into inversion. A gate voltage of minus 0.44 brings us into a situation where we're just on the brink of going into weak inversion. So for gate voltages above minus 0.44 but less than plus 0.02, that would be the realm of weak inversion. And that corresponds to points 1 and 2 in figure 18.1, all the way back, another 15 pages or so back. And just scroll through that and take a look at it. Now we can say, okay, that's a little bit extreme. You don't want to start at intrinsic. Let's start at 1.3 times the bulk. Not 2, which would be threshold, but 1.3. And then we get a gate voltage of minus 0.3 volts. So this would be considered a reasonable range for weak inversion. It's still a significant voltage interval, and sub-threshold operation is still a big deal, and it's still a big problem. And I guess just one more attack on this thing from a little bit different perspective. If you write the logarithm of the drain current, of course it's the exponential, the power in the exponential comes down. If I write it as a function not of gate voltage but of band bending, then, and I do this, it looks exactly like we had for the energy band diagram. So if the doping increases by a factor of 10, the Fermi level goes up by a factor of 60 millivolts. And that is what that's what we have here. And so from the perspective of band bending, we will get 60 millivolts per decade, just like we got in the Fermi level, moved up 60 millivolts. It took a increase in doping of times 10 to do that. However, when I convert from band bending to gate voltage, I put the M in there, and that is why the swing is not as good as it is for the BJT. Okay. So I want to skip over now to some thoughts on the regions of operation and just sum up the subthreshold operation. The quote-unquote simple theory, we have just 3 regions: accumulation, depletion, and inversion, or what we call strong inversion. And we have 2 demarcations, flat band over here and threshold over here. And that assumes that we go from basically no current whatsoever, current as in IDS, we get absolutely no drain current in depletion, and all of a sudden we get into strong inversion and we have a square law. Well, that is not terribly realistic, because things don't change that quite that dramatically. So that's why in the improved, or what some people refer to as the bulk charge theory, we added another region. So between depletion and inversion, we added weak inversion. In weak inversion, we have diffusion current, and strong inversion, we have drift current. But that's also not terribly realistic, because it says that the current somehow magically changes from diffusion current to drift current as we go from weak inversion to strong inversion. Rather, we saw that there is a slowly changing transition from diffusion to drift current, and there's a region, for want of a better term, we call it, say, moderate inversion, in which we get both diffusion and drift current. And as the gate voltage increases, we increasingly get more drift current and less diffusion current until we go into strong inversion, where everything is drift current. And just to end things off with a hopefully reasonable note about this parameter M, M appeared in 2 places: in subthreshold operation, which we just went through, and also in strong inversion. In both cases, it refers to an increase in the depletion region width. in the case of subthreshold inversion, because whenever we raise the gate voltage, we're putting some charge not only into the mobile electron inversion layer at the surface, but rather we're also putting charge into the depletion region. In strong inversion, as we move along the channel from the source to the drain, the charge balance requires that the depletion region increase. So whenever we get a depletion region increase, we have to contend with this issue of M. And it's the same M, whether we're in weak inversion or we're in strong inversion with a applied VDS. Same M. 1 plus the depletion capacitance divided by the areal oxide capacitances, and we can turn these into thicknesses of the depletion layer and the oxide layer by just flipping it, because the capacitance is inversely proportional to the thickness. So we have the oxide thickness divided by the depletion width thickness. The 3 comes because we have to include the permittivities, and the permittivity of glass SiO2 is 1/3 of that for silicon, and that's why the 3 appears here. So again, I should say naively, we'd want to say, okay, we make WD big and TOX small. Well, yes and no. TOX small, always good, because we want to have more control over what happens in the silicon by making the oxide capacitance as large as possible. Here, WD large means that the doping must be small, and for other reasons that are much more compelling, we can't do that. Okay, so that wraps it up for a weak inversion, and we can now move on to Chapter 22. In Chapter 22, there are 4 main topics. There's channel length modulation, which is we'll be introducing today. There is velocity saturation, which involves a bit of mathematics, extremely important topic for all kinds of field effect transistors. Then we'll be talking about charge in the gate oxide, which is perhaps less of a practical issue today, but is historically very important. And there's some good physics involved. So if there's good physics involved, we need to discuss it. And then we'll be wrapping it up with the Deal-Grove model for oxidation. Okay, so let's talk about channel length modulation by starting with base width modulation. And again, with BJTs, we usually talk about widths because it's a vertical device. We layer one material on top of another, and they have certain widths, whereas channel, this is in MOSFETs, are not layered, they are horizontal devices, so we speak about lengths if we're going in the horizontal direction. So if you call in a BJT, this is for a PNP structure, we have the base is more heavily doped than the collector, which means that the depletion region on the base side is thinner than the depletion region on the collector side, and they are shown here in red and orange. But as we make the reverse bias on the base collector junction higher, they both increase. So if the base depletion region increases, moves to the left, the neutral base region, which is from this junction here, which is the emitter base junction, to this point here, the neutral base gets smaller. The neutral base gets smaller, the current goes up. Okay, so that is kind of a blast from the past for the BJT. And of course, if we have different values of forward bias, we would have different curves here, and all of these curves end up, I probably should have shown this explicitly, in the quote-unquote early voltage, which we would like to make as large as possible. 60 volts is pretty reasonable, 60 or 80 volts. Okay, so the same thing happens in a MOSFET. In a MOSFET, above saturation, the pinch-off point, this is actually at saturation, the pinch-off point is right at the drain. However, if the voltage continues to increase, the saturation or the pinch-off point moves to the left and the channel length becomes smaller. Just like the neutral base becomes smaller, the channel length becomes smaller and the current goes up. So we can see that from a little bit of a different perspective by writing an expression for the ID sat, and of course it's just proportional to VD sat squared, square law, which is not really true, and we'll see why in just a little bit. We talk about velocity saturation, but we always have this coefficient here, and the L is on the bottom, and if we have a situation where we're in saturation, where the VD sat point is moved to the left, then we have to talk about L prime rather than L, and as the VD sat point moves further and further to the left, the L prime gets smaller. As the L prime gets smaller, the current goes up. So that's the basic idea, and boy, that looks pretty much like the BJT. Here's the BJT. I should have drawn perhaps another value for the forward bias emitter base junction, but have a bunch of curves. They all slope up. Here for different gate voltages, we have a bunch of curves, and they all slope up as VDS gets bigger and bigger. These are the saturation points right here. Above saturation, we get this nice curve. This is the linear region where we want to stay out of. So let's end things here. We covered quite a bit, and we will jump. Talk about this next time, and that basically will finish up channel length modulation. Not really too much to worry about, not to go over. And we'll end with a video. It doesn't need any introduction. I think you'll find it interesting, and we'll see you next time.
The monkey business illusion. Count how many times the players wearing white pass the ball. The correct answer is 16 passes. Did you spot the gorilla? For people who haven't seen or heard about a video like this before, about half miss the gorilla. If you knew about the gorilla, you probably saw it, but did you notice the curtain changing color or the player on the black team leaving the game? Let's rewind and watch it again. Here comes the gorilla, and there goes a player, and the curtain is changing from red to gold. When you're looking for a gorilla, you often miss other unexpected events. And that's the monkey business illusion.